Hey guys, what's up everyone? Welcome back to another video from the AP3X Institute of Mathematics Education. My name is Akin, your math instructor. And as I had mentioned in most of the introductions of my videos, I primarily focus on assisting students with mathematics at the CSEC, CCSLC, SEA, City and Guilds level of math. So if this is the first time here on the channel and or you want me to focus on a certain area in math for you, I can make some videos for you, my subscribers. So leave me a like, leave some comments down below, let me know what you think. And of course, this is a follow-up video to my part 1 introduction to circle theorems or circle geometry. If you haven't watched that as yet, well, it was just merely an introduction to the different lines that are affiliated with the circle and so forth and so on. Now in this video, I'm going to be looking at, just before I go into the actual content of the video, do not forget to smash that subscribe button, guys, and do not forget to leave a like on the video. It helps the video to get out there to the YouTube community, okay? Alright, so get that done for me. Let's jump right into the video. Alright, so we're going to begin the explanation of the theorems, and we're going to have some statements and we're going to have some theorems. Statements are just kind of like what I refer to as foundation knowledge to why or how the theorem exists and how it works. Alright, so as I had mentioned to you in the introduction that there are 13 theorems, of which 9 of the 13 are strictly related to the circle. And the others are supported by triangles and quadrilaterals that may be inscribed inside the circle. Hence, we use some of the geometric statements that are related to those shapes. So the theorems include a few geometric statements. Let's look at each along with some basic applied examples. Alright, so here we go. Statement number 1 is that you must remember that radii of the same circle are equal. Well, that is in fact the very important information about the radius. All right, there's going to be more than one radii in a circle, so hence, regardless of however many there may be, then they're going to be of the same length. All right, and so with that statement, now we can come up with our first theorem that states that the theorem 1 implies that if two radii of the same circle are connected, all right, if they're connected in any way, all right, then it forms what is known as an isosceles triangle. An isosceles triangle once we connect all the vertices or all the edges of the radius. All right, so basically here we can identify the radius because there's always an indicated center. So here in this diagram here, I have center O, right, and I have a point on the circumference A and a point on the circumference marked here B. So if I go right ahead here and I connect these two here, let me see if I connect these two here, then you're gonna find that the isosceles triangle is created. All right, and so what do we need to know about an isosceles triangle is that then an isosceles triangle has two equal sides, and those are the two equal sides that are going to help us to determine certain angles that may be formed within this three-sided bounded figure known as a triangle. All right, so here's an angle here, and there's an angle here, and is an angle here. So based on whatever information is presented to you in the circle, then they may ask you to find the size of this angle, or you can find the size of this angle, or you can find the size of this angle. So they can ask you to find any three. All right, and we're not really talking about the other sections of the circle, but I wanted to identify this part particularly that I have highlighted here in red. In red here represents a part of the circumference, and this part here is what we refer to as being the arc. All right, so it is the arc. All right, and this red one here is known as the minor arc, and the black one continuing around here is known as your major arc. All right, and inside here later on in future tutorial videos, if you request it, we're going to talk about this region of the circle that is known as your sector. All right, your sector, and also this part here is known as your minor sector, and everything else here is known as your major sector. All right, so that's basically the whole crevice, corners, depths of whatever this theorem entails. All right, now we're going to look at theorem number 2. All right, theorem number 2. Now, theorem number 2 talks about the intersection or the point of contact between the radius and the chord, the radius and the diameter, or the tangent and the chord, or the tangent and the radius. All right, and there's a relationship, an angle relationship between those 4 separate lines, and it says here that if a radius, which is this line here, meets a chord or a tangent, then basically we are saying that the diameter meets the chord or the tangent, then the point of intersection is 90 degrees. All right, so here we have a radius here. All right, I'm gonna label that radius here as R. I'm gonna label that radius as R. All right, and so R meets the tangent. Let's call this tangent here T, as I have it labeled here, tangent T. So if the radius meets the tangent, then you're gonna find that if you were to connect those 2 lines here, you'd form what is known as a right-angled triangle. All right, so there you can see again, like the connection of the 2 radii in a circle, which forms an isosceles triangle. If it is that the radius meets the tangent, then connecting the 2 edges of those 2 separate lines will form a right-angled triangle. All right, powerful stuff, guys, when it comes to circle geometry. We're gonna then look now at if it is that the radius is perpendicular to the chord. All right, so here is the radius. Now we're finished with the tangent. Let's look at whatever happens when it contacts with a chord. All right, and this chord, bear in mind, guys, has to be perpendicular. Okay, so you cannot have, let's say here, a radius here, and then I so happen to have a, say for example, a chord like this, like say for example the diameter. All right, this here is that the diameter here is not perpendicular to the radius, so we can't say that this is 90. All right, the key word in understanding this theorem, and a lot of students get it mixed up, is that once they see that the radius touches a chord, any chord, it's not just any chord, this chord has to be perpendicular, meaning that it has to be vertical or it can be horizontal. All right, so it's either vertical. Let me just erase here. If, say for example, that a radius heading into the direction of a chord like this or like this, then they most likely will meet at 90 degrees. Or if you have so happen that a radius is meeting the chord like this or like this, then you're going to find that at any given point you're going to meet at 90 degrees, but it cannot be diagonal. All right, so very, very important there. That's also another relationship. So you're going to find here also that a right angle triangle is created over here, and it so happens that a right angle triangle is also created over there, and also one is created down here, and also one is created down here. So you've got to look for those little triangles that are formed within some regions. All right, as long as you have lines intersecting and you're being connected by other lines, then more than likely you're going to be forming quadrilaterals, you're going to be forming triangles, that kind of thing. All right, and so here we have an example here, as you can see here, with some points. So here C, we can just look at the different sections. We can look at the fact that O to C going in this direction is a radius. Okay, you can see here also that O to D, all right, let's see here, O to D, so all the way down here is also a radius. All right, So we can see also here that P to B, all right, what would P to B be? That would not be a line. That would just be an unfinished line, okay? But we can look at the fact that AB is a chord. AB is a chord. And we can look at the fact that also CD is a diameter. All right, so there's several relationships that we can form. I could ask you several questions here on this alone if the class was in a live session, and we could just do some, you know, IQ tests based on identifying the lines within the circle. All right, and here is an example of a rather complicated appearance of the diagram, right, where we have a circle meeting the edge of a larger circle, lines connecting from one point and vertex and point of contact, creating what is, it kind of looks like a weird looking shape, and this kind of freak students out, pardon my language. It kind of just scares students when they see this, when in fact it really boils down to you just looking at how the points are connected. All right, so if we look at the fact that, say here, PQ, all right, that's a line, basically that's a tangent that is connected to both the circle, and then we have this diameter that runs through the larger circle, and then we have this secant line here. We can see it's a secant from the circle marked D, or it's a secant from the circle marked B. Alright guys, do apologize for that cut or that intervention with the video. I did get a notification that kind of cut the video short, but let's just get right back to what we were saying here, that this complicated appearance of this particular diagram here is just really two circles and a triangle connecting different parts or points within or on the circumference. So we're going to look at some questions now, as I said here, with application of theorem number 1 and or theorem number 2. All right, so here's an example. Example question number 1. Here we have a circle, yes? And we have, this is how I usually start my questions if I was in the exam. If I'm in an exam and I see a diagram, the first thing I want to do is use my fundamental principles that I learned from in the first video that I had made. So the first thing I do, and this is me as a math teacher and as a student, the first thing that I do is that I try to identify the different lines that are in the circle. That will kind of stimulate the part of my brain that will focus on that particular theorem. There are 13 theorems. It's a lot to remember under exam conditions. But if you say to yourself, for example, like I'm about to do here, that, okay, OD is a radius and OB also is a radius, that stimulates the part of the brain that brings up theorem number 1 that states that, hey, radii of the same circle are equal. Well, if those two sides are equal, then naturally the angles at the bottom are also equal. So therefore, if this angle is x, then it means that this angle is also x. And so if I wanted to find this particular angle, if needs be, then if I need to find this angle, then it would simply mean that this angle would have been 180 minus the sum of the two angles at the base. So that is negative, that is minus x plus x. So therefore, this would be 180 minus 2x. All right, and that's the formula, that's the expression that could perhaps help me later on in finding that angle. But it's clear that they're asking me to simply find the angle that is marked x. But just by me identifying the fact that OD and OB are radii, then that pretty much allows me to create an algebraic equation based on the theory that I have with angles related to the triangle. Another thing that you also want to recognize here is the fact that, AC is a diameter. Sorry, pardon me. So sorry about that. AC is actually a tangent. And if you remember when we were talking in the introduction video that the point of contact between where the tangent meets the circumference. That's called the point of contact or the point of tangency. But in theorem number 1, which you just learned, right? In theorem number 1, where we said that, or is it theorem number 2? Pardon me. We just explained it, that if a radius meets a tangent, and we can pull that screen up in a moment, all right? So here it is. If a radius meets a tangent, then it means that this angle at the point of contact is 90 degrees. So it's the same sort of diagram. It's looking almost the same way. And so you can see here that the point of contact here is 90 degrees. And that's going to be key, because this is now the actual key that we need to use to open the door to finding the angle that is marked X. Because now that we know that this point of contact here is 90 degrees, there's actually 2 ways to find X. We can find X by using the concept of angles at a point on a straight line measures 180 degrees. So therefore, if you were to say, for example here, let me just get my marker. So if you were to say, for example here, that the angles that are formed at B would have been 28 plus X plus 90, then we could form an equation and say that X then plus 28 plus 90 equals 180 degrees. We have an algebraic equation then, so we can say X plus, and then if we add 28 to 90, we should find ourselves with 118. And therefore, those two angles will sum to 180 degrees. So therefore then, if we transpose 118 to the right side, we're going to find that the angle marked X is going to be calculated by subtracting 118 from 180, and you'll find that that is 62 degrees. So the angle marked X here would be 62 degrees. We could actually find the angle marked X, which I could safely say is an easier way, or it's more or less the same. Remember, we had said that OB is a radius that meets the tangent AC at 90 degrees. So on this side here, we could actually find the angle marked X, and we could say that, okay, then 28 plus X equals 90 degrees on this side. So then X would have been equal to 90 subtract 28, which you're gonna find here that the answer is 62 degrees. So that is how you can actually use and manipulate the triangle manipulate the diagram to get the angle that you're in search of. Now, this is just basically like a guide into the thought process that goes behind you actually calculating. It's not just get up, see what the angle is and get it right. It doesn't work like that. You have to be able to manipulate and find different ways, because sometimes, for example, this question where we could use both methods to get to our answer, there's going to be some diagrams that only needs or can only be used with this method or only this method here. All right, so you could also do all of that. Another way that you could actually look at this too is the fact that since OBA is 90 degrees, then these two angles are complementary, and so complementary angles also adds up to 90 degrees. All right, so there we go. The angle is 62, and if this angle is also here 62, then we could find the angle in here. All right, so if we add 62 and 62, we're going to find out we get 124. And if we subtract that from 180, you're going to find that the angle is going to be, say here, 124 from 180. You're going to find that the answer is 156 degrees. Okay, beautiful. All right, so that's an explanation applying Theorem 1 and Theorem 2. It wasn't a difficult question, but you can see that we can get a lot from a very simple question like this. This now will supercharge our ability to look at Theorem number 3 and 4. All right, so here's Theorem number 3. Central angle theorem. This is related to an angle that is created at the center of the circle. So here now what we're looking at is the angle formed at the center of the circle is twice the size, I should have left out the word size here, is twice the size of the angle formed at the circumference that is subtended by the same chord or arc. All right, let me break this theorem down because a lot of persons get it mixed up. And when it's been explained by a variety of different math teachers, they sometimes leave out very important information, such as the fact that it has to be subtended by the same chord or arc. All right, it has to be bounded, because a lot of the times, once a student sees an angle in the center, they automatically assume that if an angle is created anywhere on the circumference, then it's going to be twice, it's going to be half the size of the one in the middle. And that's not the case, because you can have an angle that is formed at the circumference by a different chord or arc, even though there is an angle at the center of the circle. Powerful stuff, guys. Let's get into it and let's have a look. So, what has to happen for this theorem to be applied is the fact that, yes, an angle is created at the center, and you can see that we have indicated this with the letter O. All right, that's our usual way of doing that. Okay, and so an angle is formed at the center. Now, notice that the angle was formed by, say here, this radius, OA, and it was also formed by this radius, OB. And so the angle that was formed by those two radii then got connected by an arc that I've indicated here in purple. Now, this arc, or if I were to say connect this and this here and say this chord, the chord and that arc, right, that has to be the chord, or that has arc where two other lines are projected from. So another line has to be projected from the edge of that arc towards the circumference, and also another line has to be connected from the other edge of that arc towards the same point where we had initially made. And that is how we can safely say that then the angle at the center is going to be, say here, twice the size of the angle at the circumference. In other words, we can say that alpha in this case is going to be equal to 2 theta, and theta is going to be equal to half alpha, or alpha divided by 2, which alpha is the angle that is at the center. All right, another way that I find that students will often say this is that the angle that is above the center. Math teachers sometimes get a little lazy in terms of explaining the concept, find it very difficult to bring across the lesson, but it is in fact not going to always be the angle that is at or above the center angle. That's not always the case. That's quite ambiguous, and you have to be careful when you hear this. It has to be what I just explained to you here, that if the chord is connected to two radii, then it is that very same chord that has to project two different lines towards the same point on the circumference for this theorem to make sense. All right, so hopefully that is a little clear here for you. Let's look at an actual demonstration in an actual diagram here. Now, have a look at the fact that, say here, there's an angle that is marked by the symbol 2 theta. 2 theta is the angle that is at the center here. Now notice here that it is, you can almost say it's above it. You can almost say that this theta here is above the 2 theta. So if you're going to look at it that way, then yes, in this instance they are equal. But notice here that also there is a theta out here, and see that theta is not above the angle. So therefore that concludes and confirm that it's not going to be, say, ambiguous statements like the angle above the center of the angle above the angle that is formed at the center. That's not the case. It has to be that this bright chord that I highlighted here, okay, projects a line towards the center and created the angle 2 theta, and then so here it projected two more lines, same chord here, projecting two more lines towards the circumference up here. Let's call this point here A. All right, and notice that this very same bright chord here projects this line and this one here at the circumference, so we could call this meeting point B, and that's why those two angles are going to be, say here, equal. All right, so those two angles are equal, and so it is going to be that the fact that if 2 theta is the angle at the center, then the angle at the circumference is going to be theta 2 theta divided by 2, which cancel leaves us with theta. So theta is the angle here. Okay, let's have a look at a more realistic example then. Notice here that we have an angle that is formed at the center of the circle, indicated by the measurement 72 degrees, and this here angle was created by this chord here. Okay, this chord, if we connected them like so, or we could just say this arc here. Okay, so this arc projected 2 lines to the circle, to the center of the circle, but also you see that there's another line that is also running continuously. That's actually the diameter. That's the diameter. Okay, and so here the diameter is the other line that projects towards the circumference, which is why 72 degrees here is this angle at the center. Then this angle here is going to be 72 divided by 2, which is therefore going to be 36 degrees. So this angle here is 36 degrees. And so what the students also got to understand is that that's not just, there's not just one way of getting that particular angle. That is just me getting the angle marked theta by using the central angle theorem. But maybe you can break it down a bit further, because you can go back to something more familiar with you guys, known as the geometric theorems. All right, basic geometric theorems, like example, the angle formed at a point on a straight line. Here's a point that is obviously on a straight line, which we know as the diameter here. Okay, and so basically the 72 degrees here and the remaining angle on that straight line there, the remaining angle here forms 180 degrees. The angles at a point on a straight line measures 180 degrees. So if I wanted to, I could have calculated this portion of the angle here, and we could say that that is 180 take away 72 degrees, and you're going to find that the angle marked here is 108 degrees. Now, since this angle here is 108 degrees, then it means that this point here and this line is a radius. We said that that's theorem number 1. And then this also coming from the same center point here going towards the other edge of the circumference is also called a radius. Alright, and those two radii are equal, which therefore forms, according to theorem number 1, an isosceles triangle where the base angles are also equal. So alright, so we are in fact looking for the angle theta, and this is method number 2. We're not necessarily looking for this angle, but if we find this one by whatever reason, then we could safely say that those two angles are equal because it's an isosceles triangle. Now, if those two angles are equal, then it goes back to another geometric, a very well-known geometric theorem known as the angles that are formed within a triangle. Alright, so we know that a triangle has 3 angles, hence all 3 angles will sum to 180 degrees. So since I know that these two are equal, then I could safely say that, say here, theta plus 108 degrees equals to 180. Alright, so theta, which is 1 theta plus 1 theta, that is 2 theta, is equal to 108 degrees. Alright, pardon me, that's 2 theta plus 108 is equal to 108 degrees. 180 degrees, pardon me. Got a little distraction here, guys. So therefore, if we transpose the 108, we'll get 2 theta is equal to 180 minus 108. So we'll end up with 2 theta being equal to, say here, 72 degrees. So theta is going to be equal to 72 divided by 2. And that's equal to 36 degrees. Yes, it's a longer route. Yes, it may look a little bit more complicated, but the complication is only because maybe you are missing the understanding behind angles within a triangle. Very basic geometric skills. Alright, but you have two methods in which you can get the angle. As I said, you have to pick your poison. See which method is best for you. Alright, let's go to this another example here. We're going to be looking at ABC. And notice here that the angle that is formed by the arc BC creates 110 degrees at the center. And also notice that the arc BC, right, also drew two blue lines connected to the circumference. And that angle is equal to 55 degrees. And the reason why is because 110 divided by 2 is equal to 55 degrees, because the angle at the center, or the angle at the circumference here, is going to be half the size of the one at the center, considering that they're subtended or bounded or made or created by the same chord or arc. Alright, so hopefully you guys got a hang of theorem number 2 and its examples, and theorem number 3. Well, in fact, theorem number 1, 2, and 3. I'm going to bring this video to the end. Do not want it to be longer than a regular studying session. So in our next tutorial video, I'm going to be explaining to you theorem number 4, 5, and 6, as well as some examples to accompany them. Alright, so I'll see you in the next one. Bye-bye.